Go turn off the lights. Go turn off the lights. You guys are missing. That's good. I know they stole it from me. It's all right.
I'm applying for a new villain loan to go by the name of Vector. It's a mathematical term, quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah! Check out my new weapon. Hurrah-gun! Oh yes! Fires like piranhas. Never seen one before. Now you have my invention. You want a demonstration? It's so difficult sometimes to get what I'm about to say.
Why did I just show that? What do you see?
What is this?
I see arrows with both direction and magnitude. Now this picture isn't a great illustration. This one is a bit better. Oh, stink. Hold on.
Let's go back to
Why is it in this chapter? Triangle. Anyway, I see triangles. But wait a minute, where do these triangles come from?
That's a good question.
forces.
Forces acting on, in this case, some little person or people going on a roller coaster. Question. Are you thankful for centripetal motion when you're at the top of a loop and you're in a roller coaster?
Yeah.
Why?
So it keeps you so you don't fall.
Well, number one, the harnesses keep you in, but number two, the harnesses don't have to work so hard because there's another force acting against what's trying to pull you down. Gravity. So are you thankful that forces don't always work together? Sometimes they work against each other?
Yeah.
Have any of you guys ever filled a pail with water and then swung it around real fast to see if you can keep it in?
Yeah.
Interesting. What was gravity doing? Gravity was trying to pull it out, but what was centripetal motion doing?
Let's just come back
Trying
to
to
the
keep it in. Luca, where's your courage, your bravery, your enthusiasm?
Let's just stop at 6-2.
That'd be such an awesome thing.
Now, I warned you guys last week that we are going to be doing some physics-y things, right? This is our physics-y stuff, but it's an introduction. Remember, pre-cal is pre-everything else math. So we have to do some physics intro with vectors, but why are we, look, why are we doing vectors right now? Triangles.
Triangles.
Could they be right triangles? Sure, but more often than not, they're probably what? Non-right triangles, which means we can't just use the Pythagorean theorem and Sokotowa-Choshikawa. We also need law of sines and law of cosines. You guys ready? You need some more inspiration?
Yeah.
All right, we'll do one more little bit of inspiration. Isn't there a roller coaster in Despicable? Oh yeah. You can turn it off.
Yeah, can we just totally.
No.
But we've never been. It's the funnest place on earth.
Okay.
Please! Oh, my gosh, Freddy! I want to please! Oh, come on!
Night, Mom. Bye, have fun.
Sorry, dude. You can't ride without an adult.
What?
We got this, it's okay. Vectors in the plane. Now we're not going to be going super crazy with this. We're going to start super basic. Are any of you guys in regular physics right now? Huh?
I took it.
Wait, it's regular physics. You took it already, Luca?
Yeah, not fun.
A high school intro to physics is very helpful to a college physics series that you might have to take. And if you're like, oh, stink, I might have to take physics. Anything engineering, anything medical or sciencey. Not really
I was
business.
gonna do engineering, so I had to take it.
Yeah, it was a good idea.
No, Luca.
Maybe computer science?
Yeah.
No, probably
that's
not.
not. It wasn't.
Depends on what type.
Yeah, my brother said that for some physics.
So there are a lot of future careers that need education that includes physics, not focused upon physics. That's more engineering. Of course, different types of engineering. But if you guys are thinking of any of those fields at all, I would definitely get a high school intro. Calculus helps as well. Calculus helps for calculus, and calculus also helps for physics. What are you guys writing? A line segment that has both. Oh, you should be able to answer this. Direction and magnitude. Oh yeah. Without the hip thrust. A line segment that has both. We can do it. Used to represent quantities like force and velocity, like you guys kind of just saw me demonstrate with the roller coaster, gravity, centripetal force. How do you say that word? It's in my head. It's been a long time since I heard it. Centrifugal? Is that how you say it? Centrifugal force. Illustration of vector. Now here's a struggle. There's something the book does that you can't do, at least I don't want you to do. The book says, hey, all vectors, no big deal. They're bold letters. Great, so how are we going to show that? Every time you write V, just do it like this. Yeah, how do I know you don't just write like really thickly? Don't do that. Even though the bold letter is great for our book, it's not going to cut it for you guys. You need to show me a vector with a ray on top. Now you could do a double-sided arrow. Sorry, that sounds wrong. Let me show you what I mean. That's one way of doing it. You can also do with just one part of the arrow. That's a little bit more common. That's usually what I'm going to do. But some people do put both parts on that arrow. I personally don't like it, but that's okay. So anytime you guys talk about a vector, first of all, you notice it's a lowercase letter, right?
Mm-hmm.
That's one way to express a vector. But you also need to make sure to put array on top. Array, not like computer programming, array, A-R-R. The bold letter, once again, is great, but only for the book, okay? Now, when we get down to the picture down below, do you see a vector?
Yeah.
Me too! Where's the vector start? This one starts at the origin, and guess what that point is called?
Origin? Oh,
Initial.
An initial point. And since a vector shows directed movement, technically we need to think about there being like a point at the end as well. Even though there is an arrow, this is where it's unlike geometry. Geometry said an arrow denotes going on forever. Vectors say, no, the arrow just shows you which way it's headed or which direction it's pulling. Or pushing, I suppose. The arrow just shows the direction of the force, of the velocity, of whatever it is you're talking about. It does have, its length has meaning. So this one is going to be called the terminal point. Just like in geometry, we could name points. We could name, like, for instance, the initial point to be Q, and we could name the terminal point to be Q. Did I just say it both times? The initial point to be P and the terminal point to be Q. So we're not going to write that vector, first of all, as a bold letter. We're going to write it with our directed arrow on top. But there is another way to talk about vectors, not just a lowercase, hey, this is vector V. But you can also talk about it with initial point followed by terminal point to show the beginning and the end. So they mean the exact same thing, two different notations talking about the vector that you see before you. Now there's more to this. Technically this side over here is kind of called like a component way of talking about it, and this is more of a, is that linear combination? But we'll get more into that as we go on. You guys got it okay? Alright. You heard the little dude in Despicable Me mention magnitude. Magnitude. We live in California, we should know this word, yeah?
Yeah.
Why do we know magnitude?
Earthquakes.
Earthquakes! Oh, struggle. We're talking about the magnitude of an earthquake. What are you talking about?
How strong it is.
How strong it is. Think the how muchness, the how strongness, that's awkward. The strength. Another way of thinking about it is the amount of force, the speed to the velocity, etc. But all of this can be seen on a graph by the length of the vector. Now, here's a struggle. Does anybody know what gravity is measured in? Let's say you're working with meters. That's not the answer, that's just a part of it. Luca, no? It's negative 9.8. What are the units though? Meters per second squared. Okay. It's okay. It's okay. Don't stress. You don't need to write it down. I'm just showing you something for illustration. If gravity, don't write it down. Don't write down gravity. Write down your notes. If gravity is negative 9.8 meters per second squared, what length would we make a gravity vector on a graph? If length denotes or symbolizes, signifies the amount of force. Can we put meters per second squared on a graph? Give me some units that denote length, or that measure length. Inches, centimeters, feet, yards. We can do any of those. But can we do meters per second squared if that's gravity? No. So if we go to put this on a graph, here's what we would do. Let's say we have a graph, and let's say we're measuring it in, doesn't really matter, tick marks, yay. Okay. Couldn't we, 1, 2, 3, 4, 5, 6, 7, 8, I should be going down, 1, 2, 3, 4, 5, 6, 7, 8, 9. Even though gravity is measured in meters per second squared, couldn't I show this vector just by having it go 9.8 tick marks on my graph? Does that make sense? So the units are important for gravity, but for our purposes, if we're putting on a graph, we're just going to use the number, and that's the magnitude, that's the how muchness, that's the strength. We're just going to be using the negative 9.8. Wait a minute, hold on. Where's the negative?
In the, well, since it's going down, if it was positive when we go up.
Exactly, it's going down. So the negative is going down. And here's another way I could do gravity. I could actually, 1, 2, 3, 4, 5, 6, 7, 8, 9. I could also show gravity this way. Is it still 9.8 long? Yeah. And is it still pointed down? Yes. So it's the arrow that shows the negative for vectors. It's the arrow saying, oh, it's going down. Oh, that makes sense for the negative. Let me get rid of all that because all of that was just extra to say. Magnitude is a length. Magnitude is a length. So we don't have to worry about the units. That's why it can be force 1 second, it can be velocity the next. It can actually be a distance.
So then you need the starting point or the end point at least, right?
Yeah. So if magnitude is the distance or the length, distance or the length, then question, how can we describe the magnitude? There's actually a formula for it. Hold on, make sure I'm not going to write it somewhere else. Am I going to write it somewhere else? I am going to write it somewhere else. Let's not do the distance formula. Instead, let's go ahead and just do it this way. Ready? When you're talking about magnitude, you want to go ahead and put double lines. It kind of looks like double parallel lines. Or I should say double absolute value lines. Whenever you see that, or whenever you are talking about magnitude, you need to show either double lines around initial point, terminal point, showing the vector in the PQ notation over here, or double lines around the actual vector named B over here. So a little ahead of myself, I started going to distance. We'll get back to that distance idea in just a second. One last thing about vectors on this page. Vectors that have the same magnitude and direction are called equal, but here's something that we need to note. They do not need to be in the exact same location. We'll say not necessarily. And that's super important because we're so used to being tied to a graph and a graph having to be a certain way and points having to be in a certain place and not being able to move stuff around. However, vectors can be translated without changing the value at all. We might need a vector in a different position, and so if we say start with this initial vector right here, and if we instead want him somewhere over here, we can move him. It's no big deal. I shouldn't show arrows. We can move him to a different location and he means the exact same thing. We can shift them, but we have to keep them at the exact same inclination, the exact same angle, and the exact same length. But we can move them around. And that's what allowed us just a second ago, or allowed this diagram to make sense, because in this diagram, it shows gravity right here on the picture, but we can go ahead and move it and say, okay, let's have gravity acting here, let's have the net force acting here, let's have the normal force acting here. This is like a physics diagram, you don't have to understand the entire thing, but the idea is we can translate vectors around. They don't have to stay in their original position. That's kind of the idea of this equal vector description. So, what do we do if they give us two vectors and say, hey, show that these are equal, equivalent, equal, same value? Show that U and V are equivalent. Oh no! Wait, they're doing U and V with bold letters. How are we supposed to do them if we're writing down the directions? Hey, this is the first place it applies. When you guys write this in your homework, what are you going to do? Yeah. You're not going to write them bold. This is where you have to kind of just keep an eye open. I don't want you writing in bold. That's silly.
Do you have to do distance formula?
That sounds like a good idea. In order for two vectors to be equivalent, we have to have, first of all, equal magnitude. And we have to have equal direction. This is kind of introducing a couple different ideas with magnitude and direction. The question, kiddos, if, and Luca already mentioned it, if we're trying to see if these have the same magnitude, all we have to do is find each of their lengths. And how do we find lengths?
Distance formula.
Distance formula. Now some of you might be like, hey, can't we just make it a right triangle and do the Pythagorean theorem? Yep, that works too, and it'll be the exact same thing. Because remember, distance formula is really just the x length and the y length. You can do 3 minus 0. What's 3 minus 0 end up being? The adjacent side 3 squared plus y2 minus y1 for you. Oh, I'm pulling that in the D1, aren't I? Okay. This is you. I apologize. y2 minus y1, which ends up just being 2. Do you guys see Pythagorean theorem? 3 squared plus 2 squared, square rooted is the hypotenuse, which is the magnitude. So the magnitude of u equals square root of 3 squared, 9, 4, or 2 squared, 4. 9 and 4 is
13.
root 13. Now you think about v, yeah? For v, what's the distance between one x value, x2 minus x1? That's distance of 3. And then that's squared. Plus, what's the distance between one y value and the other? 2. So 3 squared plus 2 squared ends up once again being. So you can say, hey, you're root 13 also. What have we just shown? Equal magnitude, same magnitude, check. Now what do we do for the other part? Aw, stink, potatoes. How do we figure out direction?
That's pretty good.
We can look at the arrows in the first place, right?
Can we look at slope?
We can kind of look at slope. We can look at slope, we can look at arrows. First of all, are the arrows headed the same way in the sense of, what can we say that? Northeast, can we say that? Are they both headed northeast? Okay, that's good. That's a good start. But what else? Isn't direction mean equal angles? So for vector u, we need an angle, and for vector v, we need an angle. Hold on, can't we just do tangent inverse of opposite over adjacent? Wouldn't that be the direction from the horizontal of this guy? And Sean, this is basically a slope, right? Rise over run, tangent inverse. Doing the same thing for angle V, we can do tangent inverse of rise over run for him. What do you guys notice about both of these angles? Oh yeah, because their slopes are the same. So since their slopes are the same, then won't their angles be the same?
Yes.
Perfect. So we can go ahead and say, sweet. Angle U, you guys will struggle, is equal to angle V. So what does that mean? Same magnitude, same direction, therefore are they equivalent? And our answer is yes. Now what haven't we gotten to?
A lot.
A lot. So kiddos, come tomorrow ready to bust out vectors because we're going to be playing, oh dear, playing. Bye guys, we have 2 more days on this. If I were you though, start homework. See you later.